Alright, so we are continuing with the cyclic structures of sugars. That was the last thing that I said we were talking about. How when you are having a straight sugar or maybe a straight chain sugar like your D glucose that you are seeing here, how it is being converted into a cyclic sugar. The same glucose although, but it's in a cyclic structure called the D-glucopyranose. Now, it undergoes a mechanism called the hemiacetal mechanism. And the overall mechanism deals with an OH group or a hydroxyl group attacking a carbonyl carbon. So let me clean this particular aspect and show you how the hemiacetal mechanism works, especially in terms of organic chemistry, how it works. I'm cleaning this part, which is a cyclic structure, and then let's assume that you are having C double bonded, and here you are having CH2OH. This side too, you are having CH2OH. Then, if you are having an OH group or a compound that contains OH group attacking this carbonyl carbon, for instance, let's say we are having CH2OH. If this OH is attacking this carbonyl carbon, I don't want to show the mechanism here, but all what you are going to get is that you are going to have this CH2. So you are going to have this CH2O. This CH2OH that you are seeing here is the same thing as CH2O bonded to hydrogen. If you remember the organic chemistry very well, you are going to realize that this one is partially positive, partially negative. So the moment it attacks, or the moment this OH group attacks the carbonyl group, we are going to have this bond breaking off, and you are going to have the electron being moved to this to have a negative charge. So now we are going to have carbon, oxygen in a negative charge. Now this negative charge will then come and attack our hydrogen here, and now we are going to get, I don't want to really show you the mechanism because I've made a video about it on my YouTube channel. So now we'll be left with our CH2O minus, which is a partially negative. And here, because of this OH group has come to attack here, we are going to have a partially positive or a carbocation, no, not a carbocation. So now you're going to have it also coming here. And then eventually, this is what I want you guys to know, that we are going to have a carbon, an OH group, CH2OH, or CH2O, and here we are going to have our CH2OH, which was there already, and also our CH2OH. If you should have another CH2OH attacking, you are going to have this hydrogen going and to replace with CH2. So that's how it works. That's all about the hemiacetal mechanism. So you see, there's something called hemi. What I mentioned first was hemi and hemisphere. Let's say hemipolyprotic. Hemi means what? Half. You get it? So hemi means like half of the mechanism. But what I've done here is a full acetal mechanism, because now I'm having an aldehyde functional group, two aldehyde functional groups. So now let me clear it off and let me start everything again. So per what I showed you earlier, this one undergoes a hemiacetal mechanism to give it that cyclic structure. So then, this is the OH group that attacks the carbonyl group for us to have this six-membered ring. So this OH group attacking the carbonyl group will release the electrons to this. Remember, they are sharing electrons here. One of the pi bond is going to break because it is more reactive and it is having a lower energy, so it's very easy to be broken. Then it's going to release to this oxygen because of its electronegativity differences. Then, if you're having something that is very long, remember, if you're having something that is very, let's say you're having a cord that is very long and you want the tail to meet the head, like what I'm doing here. This is the tail aspect and this is the head aspect. If I want the tail and the head to meet, what do I do? For the tail to meet the end, I have to bend the cord or I have to bend the rope. So it undergoes a process called bending as well. And this bending makes this OH group more closer to the carbonyl group so that it can attack it and make the hemiacetal mechanism possible. So let me draw it again. Here we can have our C. So let's say I've bent it. Now this is my first carbon. Now this is my second carbon, my third carbon, my fourth carbon, my fifth carbon. And this, so for this fifth carbon, I'm coming to expand it. I'm having my OH here. I'm having my hydrogen here. Having my hydrogen here. Let me put hydrogen here first because there's a process to that we'll also be talking about. Yes, I'm having my OH here. Remember, on this side, we're having a OH being on the right, so the OH will come down, the hydrogen will come, our OH will come up, hydrogen will come, and then our OH will also come up, hydrogen go down. So this is what I've drawn here. I've bent it. It's still carbon 1, carbon 2, carbon 3, carbon 4. Yeah, I think there's a CH2OH here. CH2OH. Carbon 4, carbon 5, and carbon 6. So right now it might be looking confusing, but if you try and look out or check out for my video on my channel, you are going to realize that it's very simple to understand here. I have bent this particular straight chain sugar so that I can make this OH group be closer to this. You can see that now the distance between this OH and the carbonyl group is closer as compared to the one that I'm having it in a straight chain. So when this thing happens, still you could see that this hydrogen is of close proximity to this carbonyl group as compared to this hydrogen. So there's something called rearrangement, or they change in position. So you are going to have this OH coming here, this CH2 going to this side, and this hydrogen coming here. Sorry, of which I have to clean and redraw it again. So if you understand it up to this point, then I'm coming to draw it after it has changed its position for the OH to be at this position and being more closer to this. So now I'm having my carbonyl group still and redraw it again. So if you understand it up to this point, then I'm coming to draw it after it has changed its position for the OH to be at this position and being more closer to this. So now I'm having my carbonyl group still with the hydrogen, carbon, 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 carbon. And here we come, I think I'll be having my CH2OH here. I'll be having my hydrogen here. And I'll be having my OH. So now you see the OH at this particular point. And here I was having OH group down, hydrogen at the top, OH at the top, hydrogen down. Here I'm having my OH down, hydrogen at the top. So I've drawn the same thing again. But this time around, this OH is more closer to this carbon to an extent that it is of close proximity to attack it. Remember when I was talking about the hemiacetal mechanism, I said that you are going to have an OH group or an OH compound attacking the carbonyl group. So the same thing happens here, but this one is just a self-attack because you're having the OH on the same carbon or on the OH is from the same structure attacking the carbonyl group. So here you are going to have this OH. I don't want to show the mechanism here because it's not really important at our stage. So the OH is going to attack it, and when this OH attacks it, you are going to have this hydrogen going to be bonded to this. And now you are going to have this O structure that we usually see. So from this, we can have our OH at the top or our OH at the down. When the OH is at the top, it's a different configuration in all, and when the OH is also at the down, it's also having a different configuration. So now, this part, this is the only part that I want you to take notes because I'm coming to redraw the structure in the cyclic form, where I'm not going to be drawing, I'm not going to be showing the carbons, because per our lessons back in organic chemistry, we know that when you are seeing a point, it indicates a carbon or it indicates the presence of a carbon. So now I'm clearing everything, and the only thing that I want you to note here is these two. You can have the OH at the top or the OH at the down. You can have the OH at the top or the OH at the down and the hydrogen at the top. These are the two things I want you to know. So now I'm coming to draw everything again. I'm cleaning the long straight chain sugar, and I'll come to draw it in the cyclic form for you all to see. This time I have to draw it very big so that everyone becomes familiar with it. So like I said, if you see something like this, it indicates carbon. So we can have our OH at the down, or our OH at the top, and we have our hydrogen at the down. This side, we were having the OH to be at the down, hydrogen at the top, OH, hydrogen, OH, hydrogen. And here we're having our CH2OH, and here we're having our hydrogen. So this is the glucose. This is the glucose structure that I've drawn, and I hope you are all following. This is a typical example of glucose. And now, let me teach you the tricks, because some people might not be interested in learning or maybe knowing more about it. So there's no need for me to even redraw the structure again and have a situation where we are having our CH2OH at the down. If our CH2OH at the down, it also indicates something else. And in this OH group, remember, this side is a configuration. It indicates a configuration. This side also indicates a configuration. So the moment they give you a structure that you should name it, always make sure that you should check out for these 2 points. Because if there's a configuration here, this one can be alpha or it can be beta. There's a configuration here, this one can be D or L. So now, if you're having this one at the top, we are calling this one D. So if the CH2OH, let me indicate it here. If our CH2OH is at the top, then we are calling it D. If it's at the down, then we are calling it L. Very simple. So it can be D-glucose, it can be L-glucose. It will be D-glucose if you're having the CH2OH at the top. It will be L-glucose if you're having the CH2OH at the down. Now, we can also have alpha or beta. That one will be based on the position of the OH group. If you are having your OH group at the top, then we are calling this one beta. If you're having the OH group at the down, then we are calling this one alpha. So that's all what we should note here. If your OH groups at the down, we are having alpha. If your OH groups at the top, we are having beta. So now here we are having beta, and this side we are also having the D. Now let me try and show you something here. In our learning or in our nomenclature, if you see a 6-member drink, like what you are seeing here, this one is a 6-member drink. We are calling this one pyranose. So in this 6-member drink, it's a pyranose. 5-member drink is a furanose. So it's not always that you are going to have your glucose in a 6-member drink. You can have your glucose in a 5-member drink, and you are not going to name it pyranose. You are going to name it what? Furanose. So let me try and you can have your glucose in a 5-member drink, and you are not going to name it pyranose. You are going to name it what? Furanose. So let me try and take a moment and give you the vivid IUPAC name. How to go about the IUPAC name. Now, if they give you, let's say, a structure like this to name, give the IUPAC name. This one might even contain like 7 marks or 8 marks. It used to happen a lot. They just want you to know whether you understand how they name sugars. So with this, what you have to first consider is your configuration here, alpha or beta. Now you see, before we did the hemiacetal mechanism, we were having a carbonyl group, and now look at what this carbonyl group has turned to right now. This carbonyl group was just a carbon bonded to 3 different groups, and now after the hemiacetal mechanism, it has been bonded to 4 different groups. We are having it bonded to oxygen here, we are having it bonded to another carbon, another OH group here, another hydrogen. So you see, it has changed its configuration from being bonded to 3 atoms to 4 atoms. So for that matter, this carbon is also having a name. Now this carbon, we are referring to it as the anomeric carbon. Anomeric carbon. So this one will be anomeric carbon. So we check out for it, the sugar, whether it is alpha or beta. We check out for it on the anomeric carbon, because it's on the anomeric carbon that we are going to check whether the OH group is at the top or the OH group is at the down. So because the OH is at the top, we are calling it beta. So we are calling this one beta. We are naming it so beta, then a dash. Now let's check out for this side too. Is it L or D? It's a D. And now ask yourself, is this one galactose? Is this one mannose? Is this one glucose? These are the three things that you're supposed to note, because there are more that we should talk about. But if you are starting, I just want you to note these three. Is it glucose? Is it galactose? Is it mannose? This one is glucose. And you can also, memorize this particular structure because it's very easy. For this side, we don't take it into consideration. We take only this part into consideration. OH, OH, OH. These are the things that we take into consideration for us to call it glucose. So now we are having glucose, but you can't just write glucose just like that. You have to end it with gluco, because there's something that you're supposed to add to it. It is in a cyclic form. So glucopyranose. So here we have our pyranose. So beta D glucopyranose. You see, it's very simple to name. It's very simple to name. Now, this one is glucose. What if you are having a change in configuration as carbon 2? If you're having a change in configuration as carbon 2, where you are having your OH at this side and you are having your hydrogen here, then it means that the initial one that I drew and this particular structure, they are epimers because they are changing in only one configuration as carbon 2. And what did we say the difference, or maybe the relationship between a relation between sugar that is changing in configuration at carbon 2 with glucose? That one will particularly be mannose, because the other one that we drew was glucose, and now there's a change in configuration of glucose at carbon 2, so now it changes into mannose. So now this one will no longer be called glucose or gluco, but we are naming it as mannopyranose. Then if you are having the same glucose alright, let's change it back to our glucose. But then on carbon 4, there's a change in configuration. Then this one becomes what? Galactose. So we are going to name this one galactopyranose. So in our next meeting, we are going to talk more about how to be naming sugars like this. So just stay tuned and move with us as we are all moving along.
Alright, so welcome everyone to the lesson of BCME 201. And today I want to continue with the naming of the sugars, but I just want to give you guys a hint on how to name these particular sugars. We've already discussed about 6-membered ring sugars. We've talked about the 5-membered ring sugar. So this is how a 6-membered ring sugar looks like, and this is how a 5-membered ring sugar looks like. So this is the pyranose and this is the furanose. I've just projected this one in a larger form so that you can see it very well, because I want to show you some configurations, some things that we should know. Configurations such as D and L, and configurations such as alpha and beta. These are the things that I want you to know. When you reclassify a sugar to be alpha or beta, for D or L, we classify it based on the position of the CH2OH. Based on the position of the CH2OH, we use it to classify the D or the L, and based on the position of the OH group on the anomeric carbon, we use it to identify the sugar as either alpha or beta. So these are the things that I want you to note. So if you know these two things, then naming the sugar will be very easy, because you already know whether it's a 6-membered ring or a 5-membered ring. It's just up to you to identify whether the sugar is D or L, and also alpha or beta. So if the sugar is a pyranose, you know that it's a 6-membered ring. It's a furanose, you know that it's a 5-membered ring. Now, this is the anomeric carbon for a pyranose sugar. This part, which is the carbon 1, is always the anomeric carbon. So this part of it is where we are calling the anomeric carbon. So the position of the OH group on this anomeric carbon will tell us whether it is alpha or beta. So if you are having your OH here, which is down, then we are calling this one alpha. But if we are having our OH at the top, then we are calling this one beta. So this one is a beta configuration. Now, if it is a D or L, this is the last but one, which is the fifth carbon. So here, if we are having our CH2OH, then we are calling this one D. But if we are having our CH2OH here, and rather having a hydrogen at the top, then we are calling this one L. So that's the difference between the two. Let me take into consideration this, where I'm having rather alpha and also L sugar. So this is also the anomeric carbon, but for this particular sugar, if you are considering fructose, for instance, where we are having CH2OH and let's say OH here, this particular one is carbon 2. So the anomeric carbon for fructose is carbon 2. That's what I want you all to know. And this is carbon 1. So carbon 1 here and carbon 2 here. If you want to know the anomeric carbon, just know that the carbon that has been directly bonded to the oxygen, that's what you are referring to as the anomeric carbon. Because initially it was bearing the carbonyl group. Remember this one, carbonyl group. Where if we are considering this one as a carbonyl group, then this one is an aldehyde. But if you are changing this one also into an R group, then we are calling this one ketone. This is the carbonyl group and this is the carbonyl carbon. The same carbonyl carbon is here. Initially, it was bonded to only 3 different groups, but now it has been bonded to 4 different groups of atoms or groups of atoms. Look at it. This carbon has bonded to carbon 1, another thing here, another thing, and also another thing here. But in the straight chain sugar, we are having the carbon to be bonded to 3 different groups, which is a double bonded to oxygen, bonded to an R group, and bonded to another R group, which has also hydrogen if you are referring to the aldo sugars. Okay, so from this part, then this side is where we are going to consider. So if you are having our CH2OH here, then we are considering it to be D because it's at the top. And if you are having the CH2OH here, then we are considering it to be L. So I'll be taking a few examples and know how to go about it. But before that, we talked about epimers, and I just want to add another example of the epimers. So hold on and let me clean the board and let me show you something very serious here. Now look at something here. If you're having a pyranose, this is a pyranose. Let's assume that we are naming the pyranose. We can have our C double bonded. We are having our hydrogen here. Let's assume that this one is a glucose. One, two, three, four, five. And the last one, CH2OH. Alright, so we can have here to be our OH, hydrogen, OH, hydrogen, OH, hydrogen. Now, if this is a D sugar, then we are going to have our OH to be here. If it's an L sugar, then we are going to have our OH rather should be here. So let's say this one is an L sugar, so L sugar, then here we are having our hydrogen. So this one is L glucose. This is the name that we can give it to it. We can't determine whether this one is alpha or this one is beta because this one is in a straight chain until it forms a cyclic membered ring where we are going to determine the position of the OH to either be at the top or at the down. This will be the name that we are going to sustain for the meantime. So let's say mechanism where we are having our cyclic structure. So we can have our OH. So this one will be the anomeric carbon. So with this anomeric carbon, we can decide whether to put the OH at the top or at the down. But on carbon 2, it still remains the same. This is carbon 2. Carbon 2. Everything that you find on the right will definitely be at the down. So OH is on the right here, so it will be at the down. Then I'm going to have a hydrogen at the top. Then on the third carbon, we are having a hydrogen down, OH. Then on this side, here we are having our OH down, and we are having a hydrogen top. Now, because this one is an L sugar, in the cyclic form, Like I said earlier in the at the beginning of the video, if you are considering it to be L or D in terms of the cyclic membrane, you are going to check out for the CH2OH. If the CH2OH is at the down or at the bottom, something like this, then this one is an L sugar, and definitely here will be hydrogen. So to position the OH group after the Hemiacetal mechanism, we can either position our OH group here or our OH group here. Now this one is a beta configuration. So we are going to have our beta, then probably L because an L sugar, then glucose, but we can't just write glucose because that's not all. Glucopyranose, pyranose because the 6-membered ring. Now there's something I want you to note here. We can also have alpha L glucopyranose. Most of the sugars, most of the naturally occurring sugars are in the D configuration. We are not having L glucopyranose. It's very rare, but you can still have it. You can prepare it in the laboratory. But for the D glucopyranose, it's very common. And also beta D glucopyranose. It's a common sugar that we all know. But we can also have alpha L glucopyranose. Now, the reason why I just want you to have this idea is that for the alpha sugars, especially in terms of glucose, in terms of allose, in terms of galactose, those beta sugars are more stable. The reason why they are more stable is that one, look at, when we are talking about the stability of compounds, especially the stability of organic compounds, we are actually referring to the steric hindrance. Steric hindrance, and what we learned back in Chem 114, so steric hindrance. So we are talking about steric hindrance. It's the close proximity of these groups of atoms. OH group is a large molecule as compared to hydrogen. OH is large as compared to hydrogen, and OH is also large as compared to hydrogen. So if you are having this OH and this OH on opposite side of the plane of this particular sugar, at least they are far away from each other, so the steric hindrance will be less. If the steric hindrance is less, the more stable the sugar is. But let's say we put, let's say OH also at the down and hydrogen here. These two large molecules, OH is a large molecule as compared to hydrogen, so these two large molecules are close to each other, and there's going to be a repulsion, or the steric hindrance that I'm talking about. The steric hindrance here just refers to the repulsion of the molecules. If there's more repulsion between two molecules, definitely the molecule is going to be what? Not stable. So that's how we have most of our sugars to be in our beta configuration. But there's one thing I want you to know, because if you are using this one to be explaining the stability of, let's say, sugars, there's one thing I want you to know, and I want you to also find out and see, because it's something that I found out recently of which it needs some attention. So let me change this one. Let me clean this configuration. Let me change the configuration on carbon 2. If I'm changing the configuration on carbon 2, maintaining everything, then I'm referring to that molecule that I'm going to write as an epimer. And if I'm changing the configuration here from here being a hydrogen and here being OH, I've just changed the configuration of only one carbon. So the configuration as carbon 2, if you change the configuration as carbon 2 of glucose, then definitely you are going to get mannose. Mannose and glucose, they are epimers. That's what I want you to know. And they only change in configuration as carbon 2. So let's say at first what we were having was the L glucose, and here we are having L mannose. Now, if you are talking about, or if you are using the same factor, which is the steric hindrance, as our means of explanation to say that this sugar is stable, this sugar is not stable, then in terms of mannose, where you are having your OH at the top, if you put this OH also in the beta configuration, then you're also going to have a steric hindrance. So for me, I feel that in terms of all the sugars, not all the beta configurations are stable. In terms of mannose, alpha configuration is rather stable. So we can have our OH here and can have our hydrogen here. So this one is more stable. So alpha mannose is more stable as compared to the beta mannose due to the steric hindrance. That's all I want you to know. So we are going to move to the facial projection of the sugars, and it's very interesting how I want you to know this. So looking at the facial configuration or the facial projection, we all know that there are different, how I want you to know this. So looking at the facial configuration or the facial projection, we all know that there are different ways of representing sugar molecules. So if you are having this sugar, let me clear this one too. Now, okay, so now let me introduce the new epimer that I was talking about here. Then this side you are going to have our OH as well, hydrogen. Let me say this one is a D sugar, so CH2OH. This one looks almost like glucose, just at carbon 3. At this particular carbon, we have changed the configuration. So it's only one point that we've changed the configuration. So carbon 3, which is C3 of carbon, of glucose, is allose. So I'm introducing a new term here, which is also a sugar, an epimer of glucose, only changing at the configuration of carbon 3. So now, let's say this one is our allose. If you want to present it in the facial projection, if you want to change it to the facial projection, this is how we do it. First, what you have to know is that note whether it's alpha or beta. So for this particular example, for this particular allose sugar, we are having our beta configuration. So beta. And also, for this particular side, we are having our L. No, we are having a D sugar rather, because the CH2O is added. Let me indicate it here. OH up. CH2OH also up. Let me do it this way so that everyone will get the clear picture of what you are doing. Now, there is something that I want you to know. If it is L or D, you have to draw it in the straight chain. So how many carbons are we having? We are having 6 carbons in all. So you can draw it as carbon 1, 2, 3, 4, 5, 6. I hope the camera takes that part of it. If not, I have to change the position of the camera. Okay, then let me clean it in. So let me try and draw it here. I bought this small, so pardon me for that. I'll get a bigger board later. So now we are having our carbon, 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 carbon. 1, 2, 3, 4, 5. And the last one, CH2OH. Our sugar is a D sugar. So if it's a D sugar, what you have to notice is that on carbon 2, remember this one is carbon 1. So let's focus on carbon 2, carbon 3, and carbon 4. Anything that is on the right should be, anything that is down should be on the right if you are referring to the straight chain projection. So on carbon 2, you are having an OH on the, down position. So we are writing it on the right, and this side will be our hydrogen. Because we are writing allose, this one is allose, so we are still having our OH here, and we are having our hydrogen, and we are still having our OH here, and we are also having our hydrogen. Now, this is how we are going to identify whether it's a D or L. On this carbon 1, here